Have you ever wondered what lies beneath the beautiful landscapes of California? NASA's recent discovery might make you think twice about the Golden State's peaceful facade. Join us as we delve into the troubling findings about the San Andreas Fault and the looming threat it poses. The San Andreas Fault, a well-known geological feature, stretches approximately 810 miles through California. This fault marks the boundary between the Pacific and North American tectonic plates, which are constantly grinding against each other. NASA has recently issued a warning about a concerning rupture in this fault, suggesting that a massive earthquake could strike California sooner than we think. But what exactly is happening beneath our feet, and how serious is the threat? The San Andreas Fault has a notorious history of causing devastating earthquakes, including the catastrophic 1906 San Francisco earthquake and the 1989 Loma Prieta earthquake. These events have demonstrated the enormous destructive power locked within the fault, capable of causing widespread damage and loss of life. NASA's recent study highlights a particularly concerning aspect of the fault, a hidden fissure that is building up significant pressure. This fissure, running along remote areas of the fault, is not just any crack. It is a tectonic boundary where the Pacific and North American plates collide. The constant grinding of these plates has created a situation where tension is accumulating at an alarming rate. The fault's southern section, which runs through the Coachella Valley and the Salton Sea, is especially vulnerable. This area has not experienced a major earthquake since 1680, making a significant seismic event overdue. The potential for a major earthquake, known as the Big One, is a topic of concern among scientists and emergency planners alike. In addition to the main San Andreas Fault, NASA's research has revealed a new fault line parallel to the main fault, named the Salton Trough Fault. This discovery complicates the seismic picture, as this new fault line has the potential to trigger earthquakes up to magnitude 7.5. The interaction between the San Andreas and Salton Trough faults adds another layer of unpredictability to the region's seismic activity. The physics behind these tectonic movements involve the lithosphere, the Earth's outermost layer, composed of the Pacific and North American plates. The Pacific plate is moving northwest at a rate of about 2 inches per year, while the North American plate moves southward. As these plates grind past each other, stress accumulates along the fault line. When this stress is eventually released, it results in an earthquake. The unpredictability of earthquakes along the San Andreas Fault is exacerbated by its complex structure, consisting of multiple segments and smaller faults. This complexity makes it challenging to predict exactly when and where the next major earthquake will occur. Advanced monitoring systems, like the San Andreas Fault Observatory at Depth, SAFOD, provide valuable data, but they cannot yet offer precise predictions. Emergency preparedness is crucial for communities near the fault. California has some of the strictest building codes in the world, designed to make structures more resistant to seismic forces. Retrofitting older buildings to meet these standards is an ongoing priority. Public awareness campaigns also play a key role in educating residents on how to prepare for and respond to earthquakes. The potential impact of a major earthquake on the San Andreas Fault extends beyond immediate physical damage. It could lead to long-term social and economic consequences, including widespread displacement, service disruptions, and economic instability. The psychological toll on affected communities would also be significant, as residents cope with the aftermath of such a catastrophic event. The historical record of the San Andreas Fault underscores the need for vigilance. The 1906 San Francisco earthquake and the 1994 Northridge earthquake are stark reminders of the region's seismic vulnerability. These events have shaped California's approach to seismic risk management, emphasizing the importance of preparedness and resilience. NASA's warning has prompted renewed attention to the San Andreas Fault's potential to produce a Big One. The study indicates that some regions along the fault are experiencing stress buildup up to 10 times faster than previously believed. This accelerated tension accumulation is a clear indication that the fault is becoming increasingly stressed. The presence of the Salton Trough Fault adds another dimension to the threat. Located near the eastern edge of the Salton Sea, this fault line's interaction with the San Andreas Fault could potentially trigger a major seismic event. The area around the Salton Sea, including the Coachella Valley, is densely populated, increasing the potential for widespread damage and casualties. The drying of the Salton Sea, a large, shallow, saline lake in Southern California, has significant implications for seismic activity in the region. This body of water, formed in the early 20th century, has been gradually shrinking due to reduced water inflows, primarily from the Colorado River and agricultural runoff. As the water levels decrease, a complex interplay of environmental and geological processes is set into motion, influencing the stability of the Earth's crust in this area. The most direct impact of the receding water levels is the reduction of weight on the Earth's crust. Water, due to its mass, exerts pressure on the underlying crust. When the volume of water decreases, as is happening with the Salton Sea, this pressure is relieved. This unloading effect can lead to crustal rebound, where the land that was previously under the weight of the water begins to rise or shift. This movement can alter the stress distribution along fault lines in the vicinity, including the San Andreas and the newly identified Salton Trough Fault. These alterations in stress distribution are crucial because they can potentially change the timing and location of seismic events. In a balanced state, the Earth's crust can support a certain amount of stress without rupturing. However, when the weight of the water is removed, the redistribution of stress can either release pent-up energy gradually, or contribute to the buildup of stress in other areas, potentially triggering earthquakes. This phenomenon is not unique to the Salton Sea. Similar processes have been observed in other regions around the world where large bodies of water have been drained or significantly reduced. For example, the construction of large dams and the filling of reservoirs have been linked to induced seismicity due to the added weight of water altering stress patterns in the crust. Conversely, the drying up of large lakes or reservoirs can also influence seismic activity by reducing the pressure on fault lines, as is the case with the Salton Sea. The situation at the Salton Sea is further complicated by its location within a seismically active region. The sea lies near the southern end of the San Andreas Fault, a major tectonic boundary. This proximity means that any changes in crustal stress could have direct implications for the fault's behavior. The Salton Trough Fault, a recently identified fault line, also runs parallel to the San Andreas Fault and intersects with it near the Salton Sea. The interaction between these faults adds another layer of complexity to the seismic risk in the area. In addition to the geological implications, the environmental degradation of the Salton Sea poses other risks. As the water recedes, it leaves behind exposed lake bed sediments, which can be picked up by winds and become airborne, creating dust storms. These dust storms pose health risks to nearby communities, exacerbating respiratory issues and other health problems. The drying of the sea also threatens local wildlife habitats, further highlighting the interconnectedness of environmental and geological issues. The findings from NASA and other scientific studies paint a sobering picture of the seismic risks associated with the San Andreas Fault. The potential for a major earthquake is not a matter of if, but when. Communities, emergency planners, and scientists must remain vigilant and prepared for the inevitable. The lessons of the past and the insights from ongoing research underscore the importance of building a resilient society capable of withstanding the forces of nature. As we continue to learn more about the dynamics of the Earth's crust, we must also take proactive steps to mitigate the impact of future seismic events. Stay informed, stay prepared, and stay safe.